All right, so I'm Robbie. Hello, everyone. So I'm CEO and co-founder at Sedaro Technologies, and I'm going to be talking about collaborative design with Sedaro Satellite, which is our product, and OpenMBEE. So I'm kind of bringing the domain-specific, engineering tool perspective to the conversation, talking about some functionality in our platform that we developed through a small business innovation research project that we did with Robert and some of his colleagues, and just kind of demonstrate the utility of this integration, that we found from our perspective, and that we were able to demonstrate, for kind of a notional satellite engineering project. So I'll start by introducing the tools involved. That's OpenMBEE and Sedaro Satellite. I know a lot of those here are familiar with OpenMBEE. I'll get into kind of the detail required to explain or provide the context for the integration that we implemented. I'll talk about the data flows and how we integrated our domain-specific tool with OpenMBEE, which I think is very analogous to what Marcel was just talking about, that they've been dealing with and what their paper addressed. And then I'll talk about the interfaces, the user interfaces that we implemented in our tool, our web-based platform, to facilitate this integration of our models with data in OpenMBEE and via OpenMBEE with SysML models. And then I'll demonstrate, demonstrate kind of what we showed as a case study for using this new feature set. So this has overlap with what some of the things have already been talked about, just to provide, kind of the context and a simple overview here. These are the components of OpenMBEE. So, first we have the model development kits. So these are tool-specific integrations, and their primary purpose are to sync models with the model management system. So that's what we developed through this SBIR. And the model management system is, the model management system is this shared repository for our information. So it allows for storage of, of course, the structured data, and then also artifacts, and we utilize both of those capabilities. And then View Editor is a web-based tool for creating shared documentation, and we can connect, that documentation to the structured data and artifacts from the model management system. And then you won't see this in my talk, but just for completeness, the OpenSE cookbook is accessible on the OpenMBEE website, and it provides best practices, lessons learned, and guidance on how to perform engineering tasks using OpenMBEE. So now I'll get into our product and provide kind of the context behind it. In itself, it's a digital engineering or model-based engineering tool, but it's a modeling and simulation platform. So I'll start by kind of describing the challenge we're trying to address with the Sedaro Satellite platform. So what's involved in being able to model and simulate a satellite mission. So we can, of course, start with the spacecraft hardware, the subsystems of our satellite, and the orbit of our satellite. And then we have the mission architecture, which includes a multitude of things: other spacecraft, our ground stations, imaging or observation targets, whether those are on Earth or in space. And then we have the actual ConOps or more detailed operational plans for our spacecraft, the logical rules that will drive how it actually behaves on orbit. And all of these things are very closely linked to accurate integrated modeling and simulation of the mission. I forgot to mention also the environment, which includes obviously a very challenging combination of multi-physics models. So our goal with Sedaro Satellite is to provide a web-based platform where we can rapidly develop a fully integrated model of the mission that includes all of those things and allows for a very efficient, again, fully integrated modeling and simulation of our satellite mission. So we've started with the module that you see here. It's called Mission Designer. And in Mission Designer, we design, simulate, and analyze the orbit, pointing, and ConOps of our satellite mission. And then over time, we're adding these additional modules for integrating with that design information and those simulation results from Mission Designer, additional simulation capabilities. So here you see a mock-up for our energy balance module, where we'll do a time domain simulation of the power system. And then we're also developing the attitude control and thermal modules right now with Air Force funding. And our goal with this is to provide, kind of a turnkey home base for this integrated simulation and analysis capability throughout the mission lifecycle. So something that is not of the, level of resolution or fidelity that will be, for it to be kind of the end-all be-all modeling and simulation tool as you get deeper into each domain-specific engineering task throughout the project. But that is a quality turnkey home base for this this integrated modeling and simulation, such that in the early stages in a design lab, like what Marcel mentioned, a small team can do rapid and collaborative systems engineering and integrate that engineering process with these relatively high fidelity simulations given the early stage of the project. And then as we move through the project, notably into the detailed design phase, we can integrate that modeling and simulation capability with more detailed models. So for the system model, a more complicated SysML model, maybe CAD, FEA, higher fidelity versions of what we're already providing. So, maybe for orbit and more flight dynamics modeling, integration with a tool like STK. And then going through the rest of the project lifecycle, integrating with hardware in the loop testing, and then with tasking and visualization that's necessary during operations. So now we'll get into, kind of the meat of what we actually did on this project and what's interesting, I think, to this group. So the goal here was, again, to integrate Sedaro satellites, specifically the first module that we have and which is live, online right now, with OpenMBEE, and we are using the MMS repository and view editor. And these are the user stories that we're looking to support, that we supported with this prototype functionality. So first we have user one, who's the systems architect. So he's working in Cameo Systems Modeler. He's building up a SysML model of the mission. And as he does that, he's incorporating blocks from a package that we provide to our users called the SSB package, so Sedaro Satellite Block Package. And those expose value properties in Sedaro Satellite to the SysML model and allow this two-way exchange of information, of design information, via MMS. And then we have the mission design engineer. So that's the Sedaro Satellite user. So they're working in our cloud-based platform to develop a model of the mission, simulate it, and then refine the mission design based on those simulation results. And then finally, we have the documentation lead. So we assume this person's in some leadership role in the project. They're primarily seeing what's going on in the view editor documentation, which of course is incorporating design information and simulation results from Sedaro Satellite, because Sedaro Satellite is exchanging that design information and simulation results as image artifacts with MMS. So now we'll talk about the data flows and how we kind of implemented this connection to OpenMBEE and to our SysML models, which you see here in Cameo Systems Modeler. So I mentioned that the idea was to provide users with a SSB package, a Sedaro Satellite Block Package, which you can see here in the containment tree in Cameo Systems Modeler, so that they can integrate those blocks into their SysML diagram. So in this diagram, we have these Sedaro Satellite blocks. You can't read the text there, it's very small. But this one's for spacecraft body frame vectors. This one's the orbital elements of our satellite. This is the location of our ground station. This is our celestial target, the sun, which is driving some of the operational mode dynamics and pointing of our satellite. And then another satellite involved in the mission is defined over here. So we have these Sedaro satellite blocks integrated, and they're serving as that patch panel and establishing a connection to Sedaro satellite via MMS. So Cameo Systems Modeler via their MDK talks to MMS, and we exchange data with the MMS repo. And then here, this diagram here shows how we connect the data in our design capture interfaces in Sedaro satellite to MMS. So we have on the right here one of the edit boards in Sedaro satellite. This is showing segments for orbit and time and targets. And then these yellow blocks and arrows show the flow of the information to our database servers and then to MMS. So we have the orbit design for our satellite that we're, is a kind of target of our modeling and simulation here. And then we have the information for each of these target entities. So a space target, another satellite, it's our crosslink satellite, the sun, and NASA Wallops, our ground station. And that information obviously is here in our client web browser, going to our app servers via our API, and then into our database. And MMS is also connected to our app servers via our API, using the MDK that we developed, and can exchange it has read-write access to that same entity information. And then that's kind of the exchange of the structured data with MMS. And then we also have artifacts. So we use artifact storage in MMS to store and version control analytics that we provide to our users. So whenever a user simulates their mission in Sedaro satellite, we generate, automatically basically, but we organize the analytics that we provide, but we generate everything, and then they can browse through all of these interactive charts in the web interface. Each of those charts in this prototype OpenMBEE integrated version of Sedaro satellite have a stage artifact checkbox in the upper right corner. So these are some time series plots on our orbit simulation results. We can check any of those. And then when we do a commit to MMS from Sedaro satellite, that data will flow into MMS. And then if it's integrated into a view editor document, it will automatically be updated. If it hasn't been pushed yet, then the view editor user will be able to now, integrate this new artifact into their documentation. And these are the interfaces that we built into Sedaro satellite to allow users to take advantage of this OpenMBE connection and create mission versions, which is kind of the high-level single source of truth model that we have within Sedaro satellite, to a MMS project. So when they create a mission version, they can choose to create an MBSE linked mission version, we call it, and then they can put in the normal information that we provide interfaces for on one of our models. In addition to that, they select the organization and project that they want to associate this Sedaro satellite model to. And then this is the interface they'll see once they've created that connected mission version, and they can pull data from any branch that they select in the project, and they can commit data. So we've tried to implement this this version controlled branch functionality in the tool. And if they commit, they add comments obviously and have some documentation on this version of the model. And I mentioned this earlier, but all of our analytics widgets now have this stage artifact button in the upper right corner. If they've clicked that stage artifact button and they go back here and they commit to MMS, then it will be updated there in MMS. So now I will open up View Editor and show the example for that satellite mission that I mentioned earlier. So this example addresses the preliminary design of a CubeSat mission, so a small satellite mission. This is all notional design information, but we based it on an actual NASA-funded 3U CubeSat mission called Firefly. And so we have some introductory information up here, some kind of background science data, nothing that's connected there. And then we see the system model, so the work of that systems architect. And along the bottom here, those Sedaro satellite blocks that have been integrated. And then we get into these sections, which each are associated with a kind of segment of the design capture that's done in Sedaro satellite, and also is kind of how our analytics are organized. So and represent a piece of this preliminary design. And then we start seeing the links to Sedaro satellite via MMS. So anything with an asterisk here is linked to Sedaro satellite. So we can, obviously go in, make changes here, and then save the changes. And if we did that, then we could pull the update into Sedaro satellite and resimulate the mission. And when we did that, we would see updates to our artifacts. So these are the plots generated in Sedaro satellite, and they've been tied in here. So these are linked to Sedaro satellite. Then we have our targets, so our crosslink satellite and our ground station. Again, design information here that's linked into Sedaro satellite. And okay, so our simulation results for those targets. And then we get into more of the operations dynamics. So operations driven dynamics, so pointing modes of the satellite. And then in the next section, we associate those to operational modes of our satellite in our ConOp section. And we create logical rules, which are driven by the dynamics that are modeled in Sedaro satellite, which determine the active operational mode of the satellite at each moment in time in this time domain simulation. And we have some performance requirements in each section. This one's relevant to a video I'll show in a minute. So we have a performance requirement for Firefly that we spend, these particular fractions of the total, simulated mission period in different operational modes to ensure that we're collecting enough science data. We're spending enough time in comms modes to downlink that data. And we're spending enough time in a high power generation pointing mode such that, we have positive power margins. So we can create these performance requirements here as the documentation lead, and then view the simulation results that we have from our user, other member of the team that's using Sedaro satellite to compare with those performance requirements. So we have an operational mode distribution pie chart from Sedaro satellite, shows those relevant percentages that we can compare and see if we're kind of passing and meeting our requirements. So now I'll hop back to the slides here and show that video with the kind of Sedaro satellite side of things in this video here. So here I'm showing the process of actually, doing this feedback between the view editor user, the documentation lead, and the mission designer who's working in Sedaro satellite. So in this video, I've clicked the wrong button, but you'll see that I'm changing the orbital elements of our satellite. So the altitude and inclination of the orbit to try and create a design that meets those performance requirements. So we were in a polar orbit at a higher altitude, flying over the poles where there's less access to our ground station and to our crosslink satellite. The objective here is to try and increase the amount of communications that we're doing to meet a requirement that we spend a certain percentage of the mission in those communications modes, and we're able to downlink our data. So what we've done is change the design information in View Editor, then it's been updated in MMS, but we haven't pulled that update into Sedaro satellite yet. So we can see now, after pulling that updated design information in, that the semi-major axis, which is essentially determines the altitude of the orbit, and the inclination have been updated. So right now we're visualizing the, dynamics, the flight dynamics of our satellite, and seeing that we're still in that polar orbit. We haven't, resimulated with the updated orbit data. And you can see why we would have less communications access, because, our inclination has more offset from our crosslink satellite, the ISS, and we're just not going to have as frequent or as close passes over our lower latitude ground station. And sorry, I said that the design information had been updated. It hadn't been updated yet because we hadn't pulled the update. And now we should see the update there. We can re-simulate the mission. So we can see the update there. Apologize for that. We're at the lower altitude, lower inclination. And we can re-simulate. Go into our analytics and see that playback. So now we're at a lower inclination. We're getting more communications accesses. And we hope we fixed the problem that was really reflected in the ConOps kind of operational mode distribution chart. So we go to that ConOps statistics analytics board, and we see that we're now meeting our requirement. And now that we're meeting the requirement, we want to share that information with the rest of the team via our view editor documentation. So we stage that artifact and then, write a comment in here. And then we can commit that back to MMS. And then the documentation lead can just refresh the page to pull in that updated information and see that their pie chart has been updated and they're now meeting the performance requirements. So I know that's pretty simple kind of example, but I think really at a very low kind of practical level shows the significant advantages that are offered by, integrating with a platform like OpenMBE is something that was relatively, straightforward for us as a software as a service platform, and something we're looking to build on in the future. I think it's really where things are going, and this project showed us that, and I'd be happy to answer any questions.
Thank you very much, Robbie. I've seen your presentation already a couple of times, but I enjoy it every time again.
Great. Thanks, Robert.
Hi, Robbie. It's Marcel speaking. A very impressive presentation. Thank you so much for that. The question I have is, what is your business model? So how do you sustain your business with this? Can you comment on it?
So yeah, right now we're a software startup. We're kind of running off R&D funds from the government right now. We also are developing some other web-based tools for NASA on a services contract. We're kind of our business plan involves two revenue streams, or really two types of customers. We have the standard product, which will be running is running now in AWS GovCloud, and nearly anybody in the world can sign up and access the platform. But we see a significant need for the larger organizations and the government customers to provide custom solutions. So we're also kind of using the software stack that we have and the physics engines that we've developed to build, custom enterprise solutions that are either cloud-based, possibly deployed to a different cloud service, or on-premises solutions, which I think is going to be a common solution for the government customers. And that's where the conversations are going right now with them. So an on-premise solution where we can build custom modules very efficiently for the platform, or build out, custom integrations to fit within their, kind of infrastructure.
Okay, very, very interesting.
I would just like to add something, because maybe that's not obvious for everyone, but whenever in that process, whenever you make a commit to MMS and you create a new document, that's all, since MMS has element level version control and also supports branches and tags, you have everything under version and configuration management control. So when you make changes, you have the trace of all those things, which I think is a key thing in keeping those engineering decisions that you make along the way and have a trace of them. Any other questions? Okay. Well, thank you very much, Robbie.